Thanks a lot for the invitation. So I just want to study one particular case of such interpolation categories that was briefly mentioned in this morning. I want to interpolate complex representations of finite linear groups, but I don't want to use oligomorphic theory. I mean, many of the results that I have could probably be proven using these methods, but I want to be more like in the spirit of Deligne, where he works with formal objects and diagrammatic categories. So before I start to talk about finite linear groups, I want to go back to I want to stick to the rep-ST case that we have seen several times today. And I want to, and there's an old result that connects S infinity or representations of S infinity to these Deligne categories rep-ST, not using oligomorphic theory. And basically, I want to recall this briefly, and then I want to say, okay, I want to do the same, I want to have the same result for these finite linear groups. So, yeah, so here's S infinity, and I don't want to look at all representations of S infinity, I just want to look at the so-called algebraic representations that were studied by Sam and Snowden. So there's a natural module for S infinity, the C to the infinity, and I can take higher and higher tensor powers and look at all the subquotients that I get. And I call this the category of algebraic representations. So this is a symmetric monoidal category, so I think I'm fine here in the workshop. And the question is, how does this relate to Deligne's category rep-ST? And of course, now we have there's this new theory of oligomorphic groups that gives one interpretation, but there's another way to relate it, to relate these two categories. But for this, I have to replace the Deligne category by its so-called abelian envelope in case the Deligne category rep-ST is not abelian. So remember that this category rep-ST, that's abelian precisely if t is not a positive integer. And if it's a positive integer, it's neither abelian nor semi-simple, but then I just replace it by this abelian envelope. I want to formally state once what this abelian envelope is, because I think we didn't really define it yet. So this is abstract now. So I have some k-linear rigid symmetric monoidal category C over some field K, and a pair. So this is this category C, and it comes and I call this pair here an abelian envelope for C if V is a tensor category, so in particular abelian, and precomposing with this functor from this Karoubian category to the abelian category gives me an equivalence of categories between, on the one hand, the category of exact symmetric monoidal k-linear functors, V to some other tensor category, and on the other hand, faithful functors from C to A. So in other words, any faithful functor extends to an exact functor of the abelian envelope. And so these are the abelian envelopes, and one example is given in the ST case by, so if you have such an abelian envelope, it's unique up to unique isomorphism, and it was proven by Combs and Ostrich that these categories rep-ST have an abelian envelope which I denote by rep-ST-AB. Okay, so once I have these abelian envelopes, I can state the theorem that I want. Okay, maybe one more thing. So why do we care about these abelian envelopes? I mean, first of all, it's always nice to have an abelian tensor category. But also these Deligne categories usually have some universal property. We've seen this for ST, for instance. Oftentimes, usually this abelian envelope also has some other universal property. Of course, it has a richer structure, but it's not just abelian. For instance, in the case of the symmetric group, this rep-ST AB is a highest weight category. Then it will allow me to connect it to other settings of stable representation theory. And of course, this extension property is often very useful. So the question is, of course, when do abelian envelopes exist? And it's kind of a difficult problem. As I said, Combs-Ostrich did this for rep-ST in a rather ad hoc way. But this will, by the way, be also the way in which it works for essentially for the finite linear groups. But then there are general existence criteria due to Kevin. And then there's a construction due to Benson, Ettingen, and Ostrich, which is a bit more restrictive but much more explicit than these criteria due to Kevin. And so at the end, we will see that this construction of Benson, Ettingen, and Ostrich can be also applied here in our situation for the finite linear groups. Okay, so the theorem that I have in mind that I proved a couple of years ago with Barta and Entova-Aizenbud is that there's a C-linear symmetric monoidal functor from these algebraic representations of S infinity to this abelianized Deligne, to the abelian envelope. This functor is faithful and exact. And so this abelian envelope has its highest weight structure, so you can talk about standard objects and tilting objects. And it takes simple objects in this rep S infinity to standard objects, and it takes injective objects to tilting objects. And these tilting objects are the ones that are coming from this original Deligne category. So this embeds, and the image in this abelian envelope coincides with these tilting objects. So that's the statement that we proved a couple of years ago. And so basically the aim would be to develop a similar theory when you replace ST by the finite linear groups. So you talk about complex representations of finite linear groups. And of course, maybe you can do the same, or I guess you can do the same when you take finite orthogonal and finite symplectic groups, but in this talk, I'll stick completely to the finite linear case. Okay, so we have to build this Deligne category for GLNFQ, and so this is one general recipe to build such a category. Not using oligomorphic language, just very old-fashioned. So you choose some faithful representation Vn of Gn. So Gn is some infinite family of groups, like the symmetric groups Sn or GLNFQ, and n runs. Then I would like to have an explicit description of the endomorphisms of tensor powers of this faithful representation here. And so this is normally quite difficult to get a good description of these endomorphism spaces, but oftentimes there is some nice enough algebra that subjects onto this endomorphism algebra and is an isomorphism if the tensor power is small compared to the rank of the group. Right? I want some kind of stabilization ultimately, like I have for the symmetric group. And so in the symmetric group, I take the permutation representation. And if n is big compared to the tensor power, I see this uniform behavior. And then the composition rule in this algebra should depend polynomial on n, so that I can just replace n by t, where t is an arbitrary complex numbers. So by the way, I work only over complex numbers today. There's no finite fields, nothing like that. And then I define some kind of skeletal subcategory of objects 0, 1, 2, and so on, which correspond to the tensor powers. So these are just formal objects which replace or model my tensor powers of this fixed representation Vn. And I just say, okay, then the endomorphisms are given by this nice enough algebra ART. And then, of course, I take the additive idempotent completion. So that's a general recipe for building such Deligne categories. And I want to follow this recipe to get the finite linear group case. So the representation that I choose is just a permutation representation on the standard representation of GLNFQ. So you take FQ to the n, and I just take the permutation representation, so the complex permutation representation. And so in particular, if I take tensor powers of this, then this is just the permutation representation on the Cartesian product of S such copies. And now I want to introduce a notation. In a certain way, finite linear complex representations of finite linear groups mix two worlds. On the one hand, I have an FQ linear structure. On the other hand, I deal with complex representations. So if I have a sum over FQ, I write this dot on top of the plus just to keep the two apart. And also, if I have such a product here, I write it like this. So how do I describe now morphism spaces or endomorphisms of these tensor powers? Yeah, it's a bit technical, but more or less the message is that so you want to have what you want to define is a map between an S tensor power and a case tensor power of this permutation representation, and you get any such map by choosing an FQ linear subspace in FQ to the S plus K. Any such subspace will give you a map, which we denote by FR. I don't know if the precise definition is particularly illuminating or important, but the important part is really to any such subspace, I get an associated linear map, FR. And in fact, every map will come from some appropriate FQ linear subspace R. And if I choose these FRs, then composition is actually polynomial in Q to the n. So, okay, before I state this, let me give you some examples of maps that I have. So for instance here, so this is a unit object as usual. So for instance, I can send 1 to the sum of all the vectors in V. So V was the natural representation. I can send V to 1. I have some kind of multiplication map, Vn tends to Vn to Vn. This is just a Kronecker delta. I have some kind of crop product. V goes to V tensor V. Here I have a flip map. Other examples of this form, so I can take 1 to the 0 vector. I have some kind of scalar multiplication map. This dot here again signifies that this is using the FQ linear structure. And then I have some addition map. So all these are examples of maps between tensor powers, but here are just first or second tensor powers. So if there's an interpretation that I can give to these maps. So when I look at the second list of maps, so 1 goes to 0, the scalar multiplication and the addition, this basically means that this Vn inherits the structure of a vector space over Fq. And this map 1 goes to Vn, which this defines the 0 vector in this vector space. And the other morphisms, this was the first list, they give this Vn the structure of a commutative Frobenius algebra. It's a self-dual via these pairings that are defined here via evaluation and co-evaluation. Okay, so the elementary lemma is the following. So the set of these endomorphisms Vr, where R runs through the subspaces of Fq to the S plus K, it spans the space of maps. And if n is greater or equal to S plus K, then this is actually a basis. And the composition of two such maps is polynomial in Q to the n. And you can be precise, you can write down the polynomial here. I don't want to really explain what these, so this is some kind, so if you think about rep ST, there is this, you always have this factor T to the number of internal circles in your partition diagrams when you glue them together. So this number D is some kind of replacement for this. And this S star R is some subspace in, well, Fq to the S plus L that you can construct. So, but the important thing is that the composition law is polynomial in Q to the n. Okay, now you can define the Deligne category. Well, you start with objects K, formal objects, which correspond to tensor powers of your permutation representation. And then you just, as HOMs between S and K, you just take the C-span of all possible subspaces of Fq to the S plus K. Then the composition is basically like for these FR maps, just that you replace the Q to the n by T, where T is a complex number. And then there is this factor, this integer factor DRS. And so that's how you compose two such maps. You have an obvious monoidal structure by just adding tensor powers. And then you, as usual, you take the additive Karoubi envelope of this. So you add direct sums and images to idempotence, and this inherits then the structure of a symmetric monoidal category from this rule. So that's basically the recipe to build this category. So the category was previously defined by Knopp. So Knopp has this very general construction where you start with something called the regular category, and he builds a tensor category from this, or like, let's say, a Karoubian symmetric monoidal category. And one of the examples that he had was this category. And he proved the following results. So he proved that this category is abelian semi-simple if and only if T is not of the form Q to the n. So note that I somehow use a different parameterization of than in the previous oligomorphic talks. In the previous oligomorphic talks, the singular parameters for which this category is not abelian were these Q numbers. And here in my case, these are these Q to the n numbers. It is, well, it's a matter of convention. But. Okay, and then, yeah, so if you are in the Q to the N case, then you can semi-simplify your category. So this is essentially subject a full tensor functor to the usual representations of GLNFQ. And provided that you don't have one of the singular parameters, so provided that you're in the semi-simple range, Knopp also classified the simple objects, and they're just in bijection with all irreducible GLNFQ representations as n ranges to infinity.
And this is a nested union. Is it like n included?
Yeah, it is, how do you say, disjoint? Disjoint union.
Disjoint.
Yeah. Okay, so maybe I should have signified it. Yeah, it's like for rep ST. I mean, you have for rep Sn, the irreducibles are parameterized by partitions of n, and then you take the union over all. Yes. By the way, this statement extends also to the case t equal to q to the n. You just have to replace simple by indecomposable. Okay, so I want to first discuss the universal property of these categories. Basically the answer is that these categories are universal with respect to having a so-called FQ linear Frobenius space. So you take a C-linear rigid symmetric monoidal category, and we basically now take these properties that we saw for the permutation representation and make this into an axiomatic definition. So you take an object which has the following structure. So first of all, it's a Frobenius algebra. So here's a multiplication map and the units, the co-multiplication. There are these Frobenius relation, and it's a special Frobenius algebra. So these are exactly what we saw for this permutation representation of GLNFQ. And then it should be a module over the field FQ, and that means that, well, there should be some kind of addition and scalar multiplication maps, and there should be a unit vector. And then there are these should satisfy conditions that you would expect from an FQ linear vector space and so on. So some associativity, commutativity, linearity of the scalar multiplication, distributivity, and so on. And then you want, of course, compatibilities between these two types of structures. So, for instance, you would ask that these are coalgebra maps. I don't want to write these down, so I'm a bit sloppy here. These structures should satisfy some compatibility conditions, and any such object will be called an FQ linear Frobenius space in this symmetric monoidal Karoubian category. And an example is given by this permutation representation in GLNFQ. But of course, you could also take the subgroups ONFQ or SP2NFQ. They would also inherit such a structure. Okay, and the theorem is that if you have a Karoubian additive rigid symmetric monoidal category, and you have an FQ linear Frobenius space in this of the right dimension, namely the dimension should be equal to this parameter of this Deligne category rep GLTFQ, then there's this universal mapping property. So there is a unique symmetric monoidal functor from this Deligne category to C, which maps this generating object to V, where V is this given FQ linear Frobenius space.
And so do you have a version for Knopp's? So Knopp starts with some category defined over FQ, finite category defined over FQ, and constructs some tensor category. So can you do the same thing in that in reality?
No, but when Knopp defines the category for GLNFQ, he starts, of course, with the category of FQ vector spaces, right? And the category you build from this is this category. It's equivalent to ours, so it's not a new setup.
Right.
Yeah.
But it actually has a more general construction. You can start with some abelian.
Okay, no, I cannot say take any regular category and prove any kind of universal property like this. So to prove this theorem, basically what you have to do is you have to come up with a description of via generators and relations of this category. And that's pretty painful here already. So there's a lot of drawing of diagrams and whatever. So I don't think you can read off from Knopf's construction any universal properties. Yeah. No, so I think Knopf's construction doesn't allow you to read off any universal property like this. So of course you can rephrase this in the usual way. You could say, okay, there's an equivalence of categories between, on the one hand, well, such symmetric monoidal functors, and on the other hand, the category of the groupoid of FQ linear Frobenius spaces in a given symmetric monoidal category. Okay. Now, there's a related universal property in the infinite case. So I'm not working with rep GL infinity FQ now, I'm just picking a subcategory. So what is the analog of rep S infinity here? So you consider FQ to the infinity, and then you take V infinity to be basically, again, the permutation representation. So just the countable dimensional vector space consisting of infinite sequences of elements in FQ, which have finite support, so which ultimately go to 0. So that's the analog of the C to the infinity representation for S infinity. And then I have on the one hand the direct analog of this rep S infinity. You just take all subquotients of tensor powers of this CFQ to the infinity. But I can also just look at the full subcategory of direct summons. And so at least for this I infinity category, I have the following universal mapping property. So this doesn't have a good notion of duality anymore, right? Rigidity fails. So this object is no longer an FQ linear Frobenius space. But you can weaken the definition of an FQ linear Frobenius space by basically saying, okay, I don't have this unital algebra structure anymore. And what you keep then, you keep all the other axioms that make sense without this, without the unit of the algebra. And this is what we call a semi-FQ linear Frobenius space. And you can show that there is a non-full embedding of this I infinity into this Deligne category, regardless of the parameter. And this is universal with respect to a so-called semi-FQ linear Frobenius space. Of course, we would like to have a universal mapping property for this rep GL infinity also, but I think we'll get it from there. So the idea is basically, so this is maybe we have to do it. The point is that why is this category I infinity relevant? If you take its additive envelope, it's the full subcategory of injective objects in rep GL infinity. And so the idea is, of course, to then, for an arbitrary simple object or so, to take finite injective resolutions and so on, and use this property on this injective object. Okay, now, if you remember the ST and S infinity case, in the ST case, I had to replace rep ST by its abelian envelope. So the question is now, what about the abelian envelope for finite linear groups? Well, first of all, it exists, and there's an explicit description due to Harman and Snowden. This is one of the things that comes out of the oligomorphic theory. So they constructed an abelian envelope, pretty much the same spirit as for the symmetric group case, right? You have this permutation category, which coincides with the Deligne category. And there is this rep G, GL, infinity, FQ, whatever category, and which gives you the abelian envelope. And so what I want to sketch is a different description of the abelian envelope, which is closer to this Benson-Ettinghoff-Ostrich construction or this original Combs-Ostrich construction. Basically, you realize this abelian envelope as some kind of category of finite dimensional C comodules for a specific coalgebra. Little warning here, so we're just writing it up. I think everything should be fine, but before you prove the Riemann hypothesis, using this, maybe give me a call, right? So, so I'm just going to repeat now the definition that is in this Benson-Ettinghoff-Ostrich paper.
So does it mean that this abelian envelope have enough projective objects?
Yes. So in fact, the situation ultimately at the very end for rep GL TFQ is pretty similar to the ST case. Just that proofs are considerably harder.
it might be a question to Andrew and Nate. I mean, when your categories have enough projective objects, I mean, is it reflected?
I think we might know.
Mm-hmm.
Okay, so yeah, so again, I have a Karoubian rigid symmetric monoidal category, and then I have the notion of, so I have this notion of a split morphism. If it's a composition of a split epimorphism and a split monomorphism, so it's a composition of projection to a direct summand and inclusion of a direct summand. And then I call an object in T a splitting object if for any elements Q1, Q2, and any morphism between them, if I tensor with the identity morphism of X from the left or right, these two morphisms split. So it was proven then by Benson, Ettinger, and Ostrich that splitting objects form a sig tensor ideal. So this means on objects, right? So tensor ideal on objects which is closed under direct summands. With I denote the set of isomorphism classes of indecomposable objects in this sig tensor ideal S. And then you define the following co-algebra C here. And this Mascal C, that's the category of finite dimensional co-modules. And that agrees with the category of, I should say, additive functors from the opposite category of finite support. Okay. And yeah, so this is my candidate for this abelian envelope. So that's the theorem. So if you take rep GLTFQ, then this ideal of splitting objects coincides with the sig tensor ideal of negligible objects. And this category of comodules is the abelian envelope. So what Benson, Ettinger, and Ostrich did was that they said, okay, provided that certain conditions are satisfied, this category could be the abelian envelope. These abelian envelopes are somehow special because they will always have enough projective objects, and usually abelian envelopes need not have enough projective objects. So for instance, if you take the Deligne categories for rep GLT or rep OT, they don't have enough projective objects. So this construction does not give the abelian envelope in these cases, even though the abelian envelope exists. But here in this case, in the case of rep ST, and now in the case of the finite linear group, this construction works. And so what is clear is that the decisive thing that you have to do is you have to talk about these splitting objects. You have to try to construct splitting objects in these Deligne categories. And that's kind of hard. You should think of these splitting objects as the projective objects in the abelian envelope. And of course, then it's trivial that they split everything. But I mean, right now we can't even talk about projective objects. So before I want to sketch how to get the splitting property, let me just state the universal property now for this abelian envelope. So if you take a Preternakian category and you take an FQ linear Frobenius space in this Preternakian category, then there are two possibilities. So either this FQ linear Frobenius space is annihilated by some exterior power, and then this functor that you get from the universal property, it will factor through the specialization functor. So this is a semi-simplification functor. This is one property. Another, by the way, you could rephrase condition one, that this rep GLNFQ is sort of universal with respect to an FQ linear Frobenius space that is annihilated by some exterior power.
So to make sure this annihilated by some exterior power implies the dimension of Q power n. Or is it two separate conditions?
No, it's a separate condition. I think at the end it follows, but yeah, it follows. Otherwise, the universal property couldn't be true. But yeah, a priori, it's a separate condition. Or, well, if it's not annihilated by an exterior power, then this functor, this universal functor, will factor through this abelian envelope here. Okay, so how do you get splitting objects? So let's go back to the rep ST case. So that's the construction of Combs and Ostrich. So if they use special objects, which are called delta objects. And in the classical representation category, rep Sn, they're defined as follows. So just you induce from Sn minus k to Sn the trivial representation. In fact, Deligne, so these objects, they have analogs in rep St. But here, of course, when you work with rep Sn, you have only these objects delta 0, delta 1 till delta n, and then it stops. But in the Deligne category, you have these delta k for all k. And in fact, Deligne used exactly these objects to build his category. So nowadays, when we talk about Deligne's construction, we usually change history. We follow basically, I think, the approach that is in common with Nostric maybe. So Deligne used these here. These objects generate rep St as a pseudo-abelian category.
Actually, Deligne did both, but
yeah,
he likes this
most
one better.
initially he did this. Yeah. And if you're now in the non-abelian range, you take delta n plus 1. So the first delta, which doesn't have a classical analog. And then the crucial statement in the paper by Combs and Ostrich is the following. So you can consider the functor, the endo functor, tensoring with delta, and you show that this factorizes over rep S minus 1. The key point here is that this rep S minus 1 is now a semi-simple category. This restriction functor comes from the universal property. Basically, you just take this generating object here, it has dimension minus 1, and then you just add enough copies of the unit object so that it has the right dimension, namely t equal to n. And this is actually, it's a special commutative Frobenius algebra, and then the universal property tells you that there's such a functor, and I call this the restriction functor. And then there is an induction functor also given by the universal property. Actually, you should, maybe in order to construct this induction functor, it's better to not use rep St here, but something called delta objects in rep St. But anyway, so this functor factorizes. And so you want to show that this delta object is a splitting object. It splits everything. And that follows immediately once you have this factorization, because, well, then you go to rep S minus 1. In rep S minus 1, everything splits because everything is semi-simple. And that gives you the splitting property for this delta object. And in fact, this delta object for rep St generates the splitting ideal. So the splitting ideal is generated by this one object. And that means you have a complete description of the splitting ideal. And that's the key step in proving that in the St case, you have an abelian envelope. So, of course, we would just like to copy this in the finite linear case. The problem is that what you would like to take is, of course, you would like to take rep GL and then t equal to minus 1, which is a semi-simple category. The stupid thing is that this category here, so the category GL t equal to minus 1, doesn't have any obvious candidate for an FQ linear Frobenius space. So it's unclear how to get a good restriction map. And anyways, it's morally false because...
You mean q to the minus 1, yes? T equals q to the minus 1. You use multiplicative map.
Okay, yeah, I agree. But in some sense, it doesn't matter because I just need a semi-simple category. Anyone will do, but yeah, neither one will work. And the reason is, if you look at the definition of this delta object, you see this is induced from the smaller symmetric subgroup. The case that we choose here is the case where we're interested here is basically a case where k is equal to n plus 1, so that you have n minus 1, so you're on the s minus 1 case. Now, you can define corresponding delta objects for the finite linear case, but they're not induced from a smaller GL n minus k, but they're induced from a parabolic subgroup. And so it's false to take just the GL here. So in this GL TFQ case, I want to define two subgroups, the parabolic subgroups, I mean all matrices of this form, CA0B. And then there's something I call the mirabolic subgroup where C is just the identity. It's K times identity matrix. And now, oops. And I start with the left regular representation. I inflate it to representation of this parabolic by saying that this HKNX trivially. And then I have delta objects delta Kn, which are given by parabolic induction, like this, from the left regular representation. If I just look at the action from GLNFQ, this is this following description here. So these are my delta objects now. And you see they're no longer induced from a smaller GL minus K, but they're induced from a parabolic, from not really parabolic, mirabolic subgroup. So,
can you use like an interpolated parabolic subgroup?
I'm going essentially. So in other words, I shouldn't take GL, I don't know, with Q minus 1 here. I should use a Deligne category for this mirabolic subgroup or parabolic subgroup. And so, well, first of all, I can construct analogs of these objects in my category. So these are candidates now for splitting objects, at least if K is big enough. So if I'm in the T equal to Q to the N case, I would expect that delta N plus 1 is my splitting object, in complete analogy to the ST case. And can I get this factorization property? And maybe you can, but in fact, you can get something weaker with a lot less work. So, okay, so basically, we talked several times about Knopf's construction. I don't want to repeat Knopf's construction because nobody has done it so far and it's a bit technical. But let me just say, okay, you can use Knopf's construction to construct the Deligne categories for the parabolic subgroup and also for the mirabolic subgroups. I want to treat it basically as a black box, that you can do this. For those of you who know Knopf's construction, let me just say that the regular category that he starts with in this case would be the category whose objects are pairs, V, P. V is an FQ vector space, and P is a surjection onto a fixed FQ to the K. So this is the regular category that Knopf would use to construct interpolations of this mirabolic subgroup. As I said, I want to black box it. Knopf's construction gives then a symmetric monoidal Karoubian category, which I call TAKT. And very important here, this will be semi-simple whenever T is not of the form Q to the Z greater or equal to K. And of course, you can choose K arbitrary. I mean, you can choose K as big as you want. So it means you can shift the semi-simple locus further and further outside. So, as I said, Knopf's construction gives interpolations of these representation categories of the mirabolic subgroup. In fact, what it gives you, so this is a semi-simplification functor, it a priori gives you, if you really look at the automorphism groups, the representations of this transposed version. But of course, this doesn't really matter because you can just get this transposed version from the mirabolic subgroup that I want by this automorphism where you just take the inverse transpose. And so this identifies the two representation categories. So Knopf's category indeed interpolates my representations of this mirabolic subgroup. Okay, and now this is now Knopf's construction of this representation of this mirabolic subgroup. And then I have a restriction functor. It's just given by the universal property. Because you see the mirabolic subgroup still acts on FQ to the N, so I can still use the permutation representation, and I still have the corresponding object. And so this restriction functor is kind of tautological. I mean, just sends the object V to itself. Of course, then this object V, the generating object, will still have a structure of an FQ linear Frobenius space. It might have certain other features which it doesn't have for GLTFQ, but it's definitely an FQ linear Frobenius space. And so this restriction functor comes from the universal property. And so I would like to ideally prove now that if I tensor with the delta object n plus 1, in the final linear case, that is factorized, exactly like for the ST case. So I go with restriction down to this mirror-bolic Deligne category, and then I have some induction functor back up, and tensoring with delta factorizes. If you choose k big enough, this is semi-simple. So I would have, again, a factorization over a semi-simple category. But I can't really prove this. The trouble is that, you see, if you go back, if you want to have this induction functor is also constructed via the universal property. But here you are staying all the time in the rep-ST world. So you always have universality with respect to some special commutative Frobenius algebra. Now we have a different category here. We have this mirror-bolic Deligne category. And in order to construct this induction functor and to conclude that this factorizes, we would need a universal mapping property for the Deligne category here, for the mirror-bolic subgroup. And this seems to be very painful. We would have to have a description via generators and relations of this mirror-bolic Deligne category, and this seems to be unpleasant.
Also, the induction functor is not monoidal.
Yeah, well, I mean, it is here. I think if you do it in the right way, if you correspond to these delta objects. So.
Yeah, you have some algebra in this rep-ST, and kind of this functor is monoidal.
You can interpret as a monoidal functor.
Modules over this algebra, and then you compose it with forgetful functor from modules to.
Okay.
Yeah. So if you do it in the way it's written here, a priori this shouldn't be monoidal, but you would talk about so-called delta objects here in rep-ST, and then the argument why this factorizes is that, okay, if you just look at the object, the generating object, it goes in both ways to the same object, and both are symmetric monoidal functors, and by the universal property of the Deligne category, then they have to agree. That's the proof of the... So you could, in the finite linear group, you can, again, introduce the same type of algebra here. You can talk about these delta objects. The trouble is really that you're no longer in the GL case where you have an FQ linear Frobenius space which describes all the tensor functors, but you're in this mirror-bolic world, and you would need a description via generators and relations to prove a universal property, and this just seems to be very awful. So what you can do is you forget about the factorization property. What you can show is ultimately that there is an induction functor which sends the unit object in this mirror-bolic Deligne category to this delta n plus 1 object. And you're working here with pre-sheaf, so this induction functor is left to join to an exact functor, this restriction functor. And so left to join to an exact functor sends projectives to projectives. And if you choose k equal to n plus 1, then this category here becomes semi-simple. So that means the unit object is projective, and so the projective object goes to a projective object. That's kind of how you replace the splitting lemma of Komsen-Ostrich. And so once you have a projective object in the pre-sheaves over this thing, then you can use it to split everything. That's, I mean, I'm swiping a lot of things under the rug here, but this is the idea basically. So I would still expect that the factorization property holds from Komsen-Ostrich. I just can't prove it. I can prove something weaker. It's a poor mathematician's version. Okay,
I don't understand anything, but probably it's not GLT, but GLT of FQ.
Yeah, this is always FQ, absolutely, yeah. Yeah, there's, No, there's no, yeah, okay. This is always GLT FQ. Okay, and so that's sort of the key step in constructing the abelian envelope. So now I have found a splitting object in this way, and then all the other properties that are needed to construct the abelian envelope are more or less formal. This is now a splitting object, and you can show fairly easily this generates the ideal of splitting objects. So it has one generator, exactly like for the ST case, and this coincides with the negligible objects, which you can see by explicitly looking at tensor product decompositions, how the dimensions of the objects look like. Okay, so that's sort of, and I should say that maybe one last comment. I expect that this mirror-bolic Deligne category here is the right analog for rep S minus 1 in all respects. So for instance, in Deligne's original paper, he basically has a construction of the abelian envelope. He just can't prove the universal property, but he shows that the abelian, or later on, once you have Komsen-Ostrich, you can realize that the abelian envelope can be realized as some representations of a fundamental group of this rep S minus 1. I guess, but I don't really have a proof, but I think it should be more or less formal that you can repeat this construction where you replace S minus 1 by this mirabolic Deligne category. It's, there are things that have to be checked, but I would be very surprised if things go wrong here.
I mean, isn't this more or less monadicity of the junction? And
Yeah, I think it should be formal, but I'm unwilling to make a... so... Okay, so that gives you the abelian envelope, basically. Those Benson-Ettinger-Ostrich construction applies, and at the end, the description is very similar to the rep-ST case, but kind of more complicated. So what is left, basically, now, so there are a lot of things left to be done. In order to have this functor, then, that relates representations of this GL infinity and the Deligne version, you really need to develop more of this representation theory of this category rep GL infinity, the algebraic representations. So in particular, what you have to study is things like you would have to construct explicitly injective resolutions of simple objects and things like this. I should say they're partial results due to Nagpal. What you also need to you need to understand this abelian envelope better. So for instance, it's crucial in the ST case that this is a highest weight category. And I don't know good proof of this. So in the ST case, this more or less comes as a surprise. Comes in Ostrich classified blocks for rep-ST, which enables you to describe blocks for the abelian envelope rather explicitly. And you see, okay, this is like temporal leap category, and then you know there's a highest weight structure. But I'm not aware of any natural proof, for instance, that this abelian envelope has a highest weight structure, and you somehow need it. So we don't have this yet for the finite linear case. And then let me at the end mention that contrary to the ST case, we suspect that there are two different Deligne categories. There should be a bigger one. So there's ours and a bigger one. So ours is generated by these delta K objects, which were obtained by an induction from the mirabolic subgroup. But you can define also delta objects by an induction from a Levy subgroup, where you have matrices A, 0, 0, B. It seems that you get a, well, it seems, we don't know, but I would guess that you get a bigger Deligne category here. But we don't know really how to construct it. So it means that we don't have a description of like the morphism spaces, no diagrammatic description and whatever. Another viewpoint would be you take not the span, the C-span of the representation FQ to the n, but you take the C-span of FQ to the n plus its dual. And that seems to form a bigger Deligne category. And you can ask, okay, what about the abelian envelope? What about the properties there? On the one hand, you might say, okay, this is an unnatural construction because one should never look at inductions from a Levy. I mean, if your parabolic induction is just fine, why do you want to do something so stupid as inducing from a Levy? But the point why you would want to do this is that in the representation stability of finite linear groups, when you look at this world of stable sequences of or sequences that have some stability conditions under GLNFQ as n runs, there are two natural categories called VI modules and VIC modules. And it seems that the VI modules, these correspond exactly to the algebraic representations of GL infinity, and this corresponds to our Deligne category. And these VIC modules that some people really like would correspond to this bigger Deligne category. But this is more like, I don't know. It's just, and of course, one more thing that you could do is you could do everything for the orthogonal and symplectic case. But you can't do hand waving and say, okay, this is parallel. I suppose it is, but you would have.
Orthogonal, they're actually.
Yeah, they're.
Like
they're
what like in plus, minus.
That's right. Yeah. But yeah, at the end, I think many things will be parallel. You would expect that it's universal with respect to an FQ linear Frobenius space plus extra structures. Same for the orthogonal symplectic case. But there doesn't seem to be any cheap, unfortunately, doesn't seem to be any cheap way in proving this. You have to really go through the generators and relations again and check things, and that seems to be rather cumbersome. Okay, so that's it.